This is Unit 3, Thermal Systems, called Thermal Rate. Okay, we're going to be talking about how heat flows through substances. And basically, what we're talking about is how much heat energy moves per unit of time. All right, because heat doesn't flow the same through all objects. You have a spoon in something hot, like you leave a spoon in some soup. All right, that's on the stove and it's heating. If it's metal, it gets hot pretty quickly. If you have something like, let's say, that's plastic, it doesn't get as hot as quickly. All right, so heat flow rates do vary. And the one thing you need to know is that they move by molecular activity, which means the warmer something is, the more activity you have of the molecules, and they move from warm to cold regions. So in other words, they set their vibrations off and they set other molecules nearby in vibration as the heat travels through. Okay, well, the simplest equations that we have for heat flow rate, the Q, remember, stands for flow rate, and the H shows you what kind of flow rate you have. It's heat, and that's equal to heat divided by time. This is your thermal flow rate. H stands for heat energy, and T stands for time. Now, in the English, the big thing to remember is that H is in BTUs. All right, and hours is your time. Now, in English, in BTUs, if you go into the store and you want to buy a heater or an air conditioner, chances are, in the United States, it's going to be in BTUs. All right, that's what they're going to use. Now, if you were, let's say, overseas, and you went to buy an air conditioner or a heating unit, they would be in calories. All right. Now the thing is, between a calorie and BTU, calories a lot smaller, so it's not real practical. All right, but that's what they usually measure. As in the SI, you have calories, and in this case, you have time as your second, so you'd have calories per second. Okay, and what is a calorie? Well, a calorie is the amount of heat that's required to raise temperature of 1 gram of water 1 degree Celsius. That's its definition. Now, the thing you have to understand is that what we count when they say, oh, I'm counting calories, is actually a kilocalorie, which means that it is 1,000 times bigger than the calorie we're talking about here. And you can click on here if you want to see more about calories. All right, what about the BTU? BTU stands for British Thermal Unit. And it's the amount of heat required to raise the temperature of 1 pound of water 1 degree Fahrenheit. So notice we're talking about pounds and Fahrenheit. Still talking about water, though. So here I have a little thing that I included here. To buy the right air conditioner for your room, please refer to these BTU calculations. Okay, so if you go to the store to get an air conditioner, they're going to ask you, well, how big is the room that you want to cool? All right, now they're not just asking you that so that they can try and sell you a big unit or anything like that. There is actually a relationship here, and you notice that they say that if the room you were trying to cool was between 600 to 700 square feet, you would need a large air conditioner. It would have to be around 20,000 BTUs. If it wasn't, it would not cool the room properly. But if you have a really small room that you're trying to heat, to cool, it would be about 5,000 BTUs. A big difference there, and big difference in price as well. All right, and it's funny because they go on to tell you about the numbers that are based on average room size, and they tell you about the 2 windows, 1 door, 8-foot ceilings, okay, and other variables, and where they are, whether it's a kitchen or so forth. But so there is a relationship there. Okay, let's just see how this works. Find the heat flow rate in BTUs per minute and BTUs per second of an oven if the heat energy is 500 BTUs for 10 minutes. Well, you've got your Q equals H divided by T. That's actually QH. All right, and you're going to take your heat, that's your BTUs, your time is 10 minutes, and you get 50 BTUs per minute. But what if you wanted to change it so that it was a BTU per second? Well, your answer previously was that 50 BTUs per minute. You're going to multiply that by 1 minute over 60 seconds. So your minutes are going to cancel out. Take your 50 divided by 60. You get 0.83. And what do you have left in units? You have BTUs over seconds. Now another one is define the H, thermal energy. This is where you need to know what the mass of the object is, what its specific heat is, because every different material has a different specific heat. That's what the use of the word specific. It is specific to that particular material. And then your temperature change. So we're going to have H equals M. Capital C is your specific heat. That's one of those things that you would look up in a chart. And then this little thing here, that's a delta. That's a Greek letter. And the capital T is your temperature. What that is telling you is that this is a change in temperature. That means that you're going to take your final temperature minus your initial temperature. Alright, so we already went through the variables. Let's take a look at units. Your thermal energy, just like we talked about before. BTU is English, calorie in the SI. Mass for the English, alright, BTUs have to be in pounds. Mass for the SI is in grams. Now take a look at this unit here. It looks pretty messy. But one of the things that you can always tell when you have a something like specific heat, alright, that's standard. You can always tell what your units have to be by the units that are there. So you know that you're dealing with BTUs, you're dealing with pounds for mass, and you know you're dealing with Fahrenheit for your temperature. Same thing over here for the SI. You know it's going to be in calories. You're going to deal with grams and Celsius. Alright, so specific heat. How many units of heat energy required to raise 1 gram mass of a specific substance by 1 degree C? Or how many units of heat energy required to raise 1 pound mass of a specific substance by 1 degree Fahrenheit? Okay? So basically we're talking about, you know, the size is obvious there, okay? Talking about quantity difference there. But basically what they mean is they're talking about how different materials will heat. And in the chart what we have here is, as you're going from here to here, what you're seeing here is a larger heat capacity. What they're talking about is how long does that substance retain heat energy. And if you look here, you've got your metals over here. They get hot fast, they get cool fast. Alright, and you keep going along here. Alright, and what do you see? You have water over here. Alright, and basically what that means is that water, it takes a long time to get warm. But once it gets warm, it stays warm. Alright, which is very important. That's why, by Memorial Day, it's usually still pretty cool. And your water's cool. Alright, so it takes a while for it to warm up. So it might not be for a couple weeks before it's decent to swim without freezing. But towards the end of the summer, it still remains warm even though the weather's getting cold. That's what that means. And then you have going up better heat conductors. If you look right here with the things that are in red, you'll see what's happening here is what is a better heat conductor. Now that's good and bad. Okay, so if you look at these, like they make pots and pans out of a lot of these things. Okay, stainless steel, iron, aluminum, copper. I don't think you usually find too many silver pots and pans. It's a little bit too expensive. Anyway, if you look at these, what you're seeing is what gets hot faster. Like you'll see pots that have a copper bottom. That means that the copper gets hot fast. Okay, and that's why they have only the bottom has that copper layer. Alright, where that, if you look at aluminum, it doesn't get hot as fast. Okay, and that's what that means. Alright, let's take a look at a problem here. How much heat energy does it take to warm 2 liters of water from 20 degrees Celsius to 50 degrees Celsius? A couple reminders here. 1 liter equals 1 kilogram, and water has a specific heat of 1 calorie per gram Celsius degree. Okay, so we have H equals MCT, and that's by the T, we're talking about changing temperature there. All right, we're told we have 2 liters of water, so that means we have 2 kilograms, which means we have 2,000 grams. So this is going to be our mass, 2,000 grams. We have our specific heat. We're going to take our change in temperature. All right, and that's going to be 30. So you're going to have 2,000 times 1 times 30. And it's going to give you 60,000 calories. So 60,000 calories to warm 2 liters of water from 20 degrees Celsius to 50 degrees Celsius. Okay, what about heat flow rate? All right, with heat flow rate, it's going to be another more complicated equation here. Thermal conductivity, which basically means, how quickly does the heat flow through it, the area that we're looking at, the change in temperature, and the thickness. And this is our formula. All right, that's heat flow, and the H stands for heat. That's flow rate. K is the thermal conductivity. A is the area. Delta T, that's your change in temperature, and this little cursive L there is going to be your thickness. Now, an example might be if you look at like a refrigerator truck. You might be looking at, well, what should I make the insulation that's in there out of? What kind of insulation board should I use? So the size, all right, it's going to be determined by the area and the thickness of it. Your change in temperature, how warm is it outside versus how cold is it on the inside. And then the K is going to be specific to the material that you use. And that's going to tell you what the heat flow rate is. You wouldn't want it to have a high heat flow rate because you want to keep your things inside the truck cool. Okay, let's take a look at our variables here. So we already talked about those. Again, heat flow rate is going to be BTUs per hour, seconds, whatever it is you want, or calories per hour, second, whatever you want in the SI. Again, look at thermal conductivity, and that's going to be an indicator of what units you have to use. And same thing here. All right, you got feet in there, so you're going to have to use square feet here. Square centimeters here, square centimeters here. This is always the key. All right, when you're dealing with a standard like K or specific heat, they tell you what units you have to use. All right, let's take a look here at a problem. What's the heat flow rate of a 70 square foot wall of plaster? Has a thermal conductivity of 0.5 BTUs inch per feet hour Celsius degree. The wall is 5 inches thick, and that is 40 degrees Celsius on the outside and 60 degrees Celsius on the inside. So let's see what we're going to have. It's feet squared. All right, so that means that's area. All right, it says your thermal conductivity. It's 5 inches thick, so that's going to be your L. And you're going from 40 to 60. So the difference between 40 and 60 is going to be 20. All right, Celsius degrees. So let's put it in our problem here. We have Q equals K, which is your 0.5. Area, which is your 70 square feet. Your change in temperature, which is your 20 Fahrenheit degrees. And then divide that by your thickness of the plaster, which is 5 inches. All right, so what happens here is everything's going to cancel out except BTUs per hour. And you end up with 140 BTUs per hour. All right, now where would you use this? Why would you want to know this? In many places, HVAC, which is an excellent career choice. All right, it's heating, ventilation, and air conditioning. You'd be using this stuff all the time. Plastic molding. All right, if you are looking at working at the plastics plant in Ono. All right, they have the plastic molding plant. You would need to have this type of information. Cooking. You like to cook? What kind of pots and pans are you going to buy? What kind of utensils are you going to keep in the kitchen? What you're doing is you're really deciding on cookware. All right, and usually most cooks look at, well, how fast they want something to cook and so forth. Thermostats. Okay, thermocouples. We've talked about those before. Where do you put